Today, dear participants of the conference, with your permission, I present a work, Helicopters, Aircraft Engines, Self-Organizing Neural Network Automatic Control System. The process of ensuring the stability of the operation parameters of helicopters, aircraft, turboshaft engines, TE, by maintaining the required stable compressor rotor speed and the dosage of fuel supply to the combustion chamber has always been a difficult task. A block diagram of a multidimensional automatic control system for helicopters, aircraft, turboshaft engine using the TV3117 aircraft engine as an example, is proposed with the inclusion of N integrators in the system, one in each of the N channels of the control system, implemented in the form of a multi-mode neural network controller using a dynamic recurrent neural network based on a perceptron, which provides control of the object subject to the following requirements for the synthesized automatic control system: aesthetism, zero static error, physical implementation of the neural network controller, stability and given quality of control processes on a fixed set of modes of engine operation. Minimum complexity of the multidimensional neural network controller. The requirement of the physical capability of the neural network controller to be implemented in the basis of the assumption that a dynamic recurrent neural network based on a perceptron intakes as a neural network. According to the developed concept, the actuating mechanism and turboshaft engine were considered as a single whole, an invariable part of the system. This approach has proven itself in the synthesis of the turboshaft engine control algorithm for helicopters of civil aviation or transport aviation. For such control object, the dynamic process in the fuel system processed much faster than in the engine. Therefore, the influence of turboshaft engine was simply neglected. But in turboshaft engine, transient processes in the fuel and engine assembly occur almost simultaneously. This statement has been repeatedly confirmed by the results of full-scale tests. On the basis of the foregoing, we single out the turboshaft engine and actuating mechanism directly into separate links, the fuel metering unit, and modify the structure diagram of the automatic control system shown in this figure. On this figure shows the automatic control system turboshaft engines diagram developed in this work. In the logical block, the input signal are analyzed as follows. Acknowledge base is built of the basis of experimental data and conclusions. In relation to it, membership functions are formed for the input parameters of the logical block as well output signals. Professor Valery Petunin made a significant contribution to the synthesis of logical dynamic systems of automatic control of gas turbine engines based on the coordination and adaptation of control channels. According to Valery Petunin, the block diagram of a separate channels of automatic control system turboshaft engine has this form. One shows a block diagram of the proposed self-adjusting neural network control system for helicopters turboshaft engine with unconnected coordinates. The control error vector after the compation elements in FET to the input of the neural network and the weight correction block, in which, depending on the signal control error vector and each discrete time, the weight coefficients of the neural network are adjusted networks. The vector of output signals from the output of the neural network in the control one and is fed to the input of the control object, helicopter, aircraft, turboshaft engine. The network is characterized by the number of neurons in the inner layer, layer 1. The structure of multilayer neural network is shown in this figure. On this figure, the diagrams of transient processes in the system during testing set the impact without preliminary self-tuning according to the model curves 1 and 2, and with preliminary self-tuning curves 3 and 4, cued often at the initial stage of self-adjustment, when the neural regulator is first switched on in the control loop. Large outliers of controlled values from the set values are observed, curve 1. This is due to the fact that when the neural regulator is turned on, the weight coefficients of the neural network are initialized randomly. In this case, there is a possibility of organizing positive feedbacks, which are the source of too large deviation of controlled values at the initial stage of self-tuning. The occurrence of such a simulation can lead to emergency situation of the helicopter. Neural network control system for helicopter turboshaft engine works out quite well both external disturbing influences, figure A, and setting influences, figure B, as well as antiphase setting action, figure C. In a neural network control system, as in classical systems, cross channels have a significant impact on the quality of regulation. With the discrete in the influence of cross-links, the quality of regulator improves significantly. The results of training the neural network according to the accuracy and loss indicators are shown in figure. As can be seen from figure, the accuracy indicator approach 1 and loss indicator tends to 0, which indicates the high accuracy of the model and its minimal error. This figure shows the results of modeling the automatic control system for TV3117 gas turbine engine based on a self-adjusting neural network control system, from which it follows that the use of the developed automatic control system increases the accuracy of modeling transient processes in the gas turbine engine control system, the diagram of which are close to the standard. The conclusions are presented on this slide. Thanks for attention.